that few minutes back.
Yes, sir. We have got the mail. Thank you.
Thank you.
Yeah. Right.
So we'll continue on the first order systems that we were talking about.
Recording in progress.
Yeah, we'll continue on the first order systems that we are talking about. So we said that we'll take examples from mechanical, electrical, thermal, and fluidic domains. And last class, I had talked about this example of a spring mass system, spring damper system, which is a first order system, and it's a mechanical system. And we had talked about its response. So today we'll first talk about electrical, thermal, and fluidic systems. And then slowly we'll move on to second order system. So first, let us talk about an electrical system. So this is the typical electrical circuit that we are talking about here. It is called an RC circuit. So we have a power source and we have a power source and we have a resistor and a capacitor. Okay. So you have a current I subscript R, which is going through the resistor. And the voltage drop across the resistor is VR. Similarly, you have a current I subscript C going through the capacitor, and basically you have a potential difference across the capacitor, which is VC. Okay. So this is called the RC circuit, and you can write an expression for this potential drop across the resistor VR as the current IR times the resistance R, as you can see here. So this is the voltage drop across. You can also write the current through the capacitor. So typically, you know that for a capacitor, Q is equal to C into V. And if your voltage is changing with time, then you can write that C into dVC over dt. So this is basically per unit time, which gives you current instead of charge. So Q is C into V, but if V is changing with time, then it becomes current. So IC is C into dVC over dt. Now, it is a closed system. So this current IC and IR should be the same. So, it is a closed system. So your voltage drop across the capacitor and that across the resistor have to be the same. Your VR and VC have to be the same. And your current IC and IR should be the same, but it should have the opposite sign. Okay. Because the potential drop across the capacitor, what is the direction of the potential drop would be opposite to the direction of the voltage drop across the resistor. So the current direction will be equal but opposite sign. So from there, you can say that your IR plus IC equal to 0. And the current through the resistor is VR over R. And similarly, the current through the capacitor is basically from here, C into dVC over dt. So these two, when added, is 0. Okay. And since you have only two things here, VR and VC, so they are equal. And so instead of VR, you can write VC here. And so you basically then multiply with
Sir, hello. Sir, your voice is cut. Hello.
On mute.
Yeah.
I think there was a signal problem. I don't know when I lost you.
Sir, in the first order only, sir. The first order.
Okay, are you able to see my screen?
Yet to come, sir. Yet to come.
Okay.
Not yet come, sir.
Okay, let me check. So
Now it is. Now it is
see my
okay, sir.
screen? So we were talking about this system, right?
Yes, yes. Yes, sir.
Yeah. So I was saying that you have a capacitor and you have a resistor, and the voltage drop across the capacitor and that across the resistor are same. But the currents, although they have the same magnitude, but they will have opposite directions, right? So the sign will be different. So your IR plus IC is 0, and IR you can write it as VR divided by R, and IC you can write it as C into dVc over dt. So these two, when added, giving you 0. So when you multiply R to this equation, this becomes RC into dVc over dt. And when you multiply R, this is VR, but then VR is equal to VC. So plus VC is 0. So this equation is similar to this first order equation. Okay. So if you compare, here you have, this is a typical first order equation. You have the time constant times d of the response over time plus the response at a particular time instant is 0. So if you, this is analogous to that. So you have basically the time constant as R into C. And this is in electrical engineering called the famous RC time constant. Okay. And a solution to this, as you know, is basically yt equal to y naught into e to the power minus t over tau. That is the general solution. But here we are solving for VC, voltage drop across the capacitor with time, how it changes with time. So that will be equal to, you have V naught times E. This is like a constant, right? So C into e to the power minus t by tau. Now when time t is 0, this term becomes 1, e to the power 0 becomes 1. So your voltage across the capacitor VC at time t equal to 0, let's call it V0. Okay. And so your VC as a function of time will be V0 e to the power minus t over RC. So essentially, let's say you have a charged capacitor with some potential VC, right? And then you connect that to the resistor. The question is how that voltage is going to drain with time, right? Initially it is V0, but when time progresses, when t tends to infinity, then this term is going to be 0. Okay. So this will be 1 over e to the power infinity. That means V naught divided by infinity. So this will become 0. Okay. So it starts from V0 and becomes 0. So if you take an example that the capacitance is 100 microfarad and your resistance is 1 mega ohm, then what is the time constant? It will be R times C, right? R is mega ohm, 10 to the 6. This is microfarad. So you have 100 into 10 to the minus 6 farad. So essentially you have 100 second is the time constant, because 10 to the minus 6 here, 10 to the 6 here will get cancelled. So you have 100 second is the time constant. Okay. So basically this is 100 second. Now, if you want to say that my t is equal to tau, okay, that means you have e to the power minus 1, that is equal to basically 0.37. Okay, so basically the capacitor will take nearly 100 seconds to decay to its 37% of initial value, because your initial value is V0. So Vc at t equal to tau divided by V0 will be e to the power minus t over tau. When t is equal to tau, this is e to the power minus 1, that is 0.37, right? So basically, it will take 100 seconds to decay to its 37% of its initial value. Next, we take an example of a thermal system.
Sir, can I ask one question, sir? I'm sorry. It's a
Yeah.
very, like I would say that, sir, this type of the order of system, I could gather that it stores energy and decay with the time in that sense, right, sir?
Yeah.
So my question is that, sir, how these are related to my measurement system in that sense? Like, I'm not able to connect this to what I mean to say, sir.
Yeah. I think for now, you
Ji.
need to basically wait until the measurement systems come, because I have to teach now the temperature measurement immediately. So as I said, when you have a thermocouple, okay, let's say it is measuring 25 degrees centigrade. Temperature of the surface is 25 degrees centigrade. Now suddenly you change the temperature to 30 degrees centigrade. Okay. How much time it will take for your thermocouple to reach 30 degrees centigrade? How do you estimate?
ठीक है, sir. Okay, thank you.
Okay.
Got it, sir.
Now the second question. Let's say your pressure transducer is exposed to some kind of source, right? Fluid source. Let's say the pressure inside the fluid is some 10 kilopascal. And due to some process, the pressure has now changed to 15 kilopascal. How much time it will take for your transducer to display the new pressure? So this is the characteristic that we are trying to understand through first order systems. Okay. So the practical implications are going to come. And second is this pressure transducer, pressure measurement that I'm talking about is a second order system. As you see, when we discuss about manometer, we have to take that system as a second order system. But the temperature thermocouple thing that he talked about is basically a first order system. So you have to learn the fundamentals of first order system, second order system in order to understand and appreciate the different measurement tools. Okay. So unless you know the basics, you will not be able to appreciate that.
Right, sir. Thank you,
It
sir.
is very important to understand these basics.
Right, sir.
So this is again a thermal problem, right? We are talking about how it is useful. This is how it is useful. So you have you are trying to analyze how the temperature of this bulb is changing with time, okay, or getting equilibrium with the environment, okay. So you have a bulb, so you have heating here, and then you have the bulb surface, and then ambient is at TA, okay. So you can create a thermal model of this electric bulb, okay. So the bulb will have some thermal capacitance, right, because of the material itself, inherent material. The bulb temperature is TB, okay. And so there is some stored energy inside the bulb due to this capacitance. Okay. And you have some temperature of the bulb. Now the ambient is at temperature TA. The bulb and temperature, the ambient, are interacting thermally through some kind of resistance RB, right? That is depending on the material of this glass encapsulation. They are interacting through this RB. Okay. So this kind of situation, which is in a typical lamp bulb, can be analyzed by taking this as a first order system. Okay. So you use what is called Lambda model. And so that is how you are able to go from this physical model to a thermal model. And you make certain assumption. You say that everywhere inside, inside the bulk, the temperature is TB, and the energy that is inside here is related to the thermal capacitance. And outside the temperature is TA, and they are interacting through some resistance, which is RB, that is the glass material, right? So we have to do energy balance. Okay. So the change in the thermal energy, basically that happens from inside of the bulb to outside, is by heat flow. Okay, and then you can write that expression for heat flow, that is QB, is the rate of change of energy of this system. Comes out as heat, QB. That is equal to the capacitance of the bulb, CV, times the rate of change of temperature. Okay, basically the heat flow, which is nothing but the rate of change of energy of the bulb, is capacitance time the rate of change of temperature of the bulb. Okay. Now, from this thermal model, using Fourier law of heat conduction, right, that this heat flow is a consequence of this temperature difference. So you can write QB equal to TB minus TA divided by the resistance. So you can write here that the heat flux QB is basically the temperature. I mean, here it has written that ambient is at higher temperature, but depending on whether ambient is higher temperature, the bulb is at higher temperature, you can use either TA minus TB or TB minus TA. And now here the temperature of the bulb is decreasing with time. So that means dTB over dt will be negative, right? So CB into dTB over dt will be negative, because this gradient, temperature is decreasing with time, means the gradient will be negative. So in order to make these two, the sign to be consistent, you have written TA minus TB. Okay, because this will also be negative, this will also be negative. Actually, TB is higher than TA, so this will be negative. So, and this gradient is negative, so they are of same sign. Now, if you rearrange this equation, okay, and you write that you define some parameter T, which is TB minus TA. Okay, so if TB minus TA, TA is fixed because ambient temperature doesn't change with time. So T is TB minus TA. So your dt over T temperature over D time would be simply dTB over dt, because dTA over time will be 0 because TA is constant. So dTB over dt you can replace as dt over dt, right? So you have RB into CV into dt over dt plus TA minus TB is basically minus T. And when it comes to the other side, it becomes plus T, that is equal to 0. Now this equation here is analogous to the first order. general first order equation is this. Tau dy over dt plus y is 0. So basically, your time constant in this situation, for the electric bulb situation, is Rb into Cv. Okay, the resistance of the bulb into the capacitance of the bulb. And let's say at time t equal to 0, the temperature was T0. So the response is something like this. Your temperature would decay with time t, that is equal to T0. When time t equal to 0, that is T0, and e to the power minus t over RBCV. Okay, so that means, let's say your electric bulb is on and you switch off. Okay, initially the temperature was T0. Now we have switched off the bulb. Ambient is at TA, bulb is at TB initially. Finally, everything will become TA, right? It will eventually cool down. Now, how much time it will take to cool down is given by this expression. Okay. Let's say you have some, in some process, you have some item, you have kept it inside a thermal oven. Okay. So let's say the temperature, some furnace you have used to keep some parts, and you bring out to ambient for cooling, or you submerged in water for cooling, and you want to calculate how much time it will take to cool. So you must use this expression, okay, to know when it will reach the part which was initially in a furnace or oven at a very high temperature, how quickly it will reach the ambient temperature. So this theory is going to tell you. So that way it is relevant to measurement. So the bulb temperature, in fact, if you were to do experiment, you can either put in a thermocouple on the surface of the bulb, or you can use an infrared sensor, right? You can have an IR camera capturing the surface temperature of the bulb at different time points. Okay, and then you can get the data. So this is one such experimental data, right? So initially the temperature was 101.2 degrees centigrade, and the bulb was turned off at t equal to 0. And you can see that as time progresses, in about 14 minutes, the temperature has gone down to 29.4 degrees centigrade. Okay, let's say it is the ambient temperature. Now, if I plot this, y-axis temperature, x-axis time, then my data is showing this curve. Okay, and I see that in about 14-15 minutes, it is reaching the ambient temperature, the cooling time. Okay, so as we know, as we have studied in the previous class, for a first order system, the system reaches steady state at about 5 times the time constant. Okay, so the 5 times the time constant is about 15 minutes. Okay, so the time constant is about 3 minutes. Okay, so the time constant of this system is about 180 seconds or 3 minutes. So for any thermal system which are first order in nature, you can do a similar kind of measurements, experiments, and express and plot them, the temperature with time. And when the time is reaching steady state, you note down the time, divide by 5 will give you the time constant of the system. So you can actually characterize the system. Okay. Okay, so this is considering a fluid system. So we talked about an electrical system, we talked about a thermal first order system. Now let us talk about a fluidic system which is first order.
Sir, one question.
Yeah.
All thermal systems, like what I mean to say is, which has, like, suppose, which are like the process of heat loss by process of radiation, will come under first order only. Or
See, if you look at here, we have made certain assumption. See, for example, here we say that the block is insulated on 3 sides so that heat flow through those sides are 0, right? In this thermal model, we did not talk about radiation, right? We only said that it is only in one direction, okay, through the resistor. There may be some heat that is going into the base and going by conduction on which you have kept it and all that. There may be some radiation effect coming. So if you include those things into this equation, you will see that the corresponding equation is no longer a first order equation. Okay, it has become a higher order equation. So this is a simplest system. That is why we are saying it is a first order system. But depending on your problem, the situation can be more complex. You may have a second order system, thermal system also. So to answer your question, not all thermal systems are first order. This is a simplified situation and which is a first order system. Okay.
thank you, sir.
So here we have a tank which is initially filled with some liquid up to a certain height h. And we have a pipe which is connected, and the liquid is basically draining through this pipe. Okay. And we want to know how this height of this liquid is changing with time, and how the flow rate that is coming out of this pipe here is changing with time. That is our main objective. How the flow rate that is coming out of this thing is changing with time. Now, if we assume that the fluid here has a density rho, and the pressure at the inlet here to the tube, inlet to the tube is P subscript T, you can write that the pressure here, P subscript T, will be the atmospheric pressure here plus rho G into H. Okay. This is simply hydrostatic pressure plus the atmospheric pressure is the pressure here. Pressure at the outlet here is PA. Okay. Now, if you want to know the pipe volumetric flow into the tank, okay, this is very important. How much flow is coming into the tank? Here, flow rate is going out. So into the tank is basically negative of what is coming out, right? So QT that is coming into the tank will be PA minus PT divided by R. Okay, so which is negative of PT minus PA divided by R. Now that will be equal to minus of rho into G into H, because here you can see PT equal to PA plus rho GH. So PA minus PT is minus rho GH divided by the resistance. R is basically the hydrodynamic resistance from here to here. Like electrical resistance, you talk about hydrodynamic resistance, which is basically a property of which basically is dependent on the geometrical parameter of this tube, the diameter of the tube and the length of the tube and so on. Okay. So once you know the resistance, you can find out what is the QT. You have another condition that whatever volume of liquid that comes out here causes a change in the height of the liquid inside the chamber here. So basically dH over dt is equal to QT divided by A. Okay, so this is the velocity at which this liquid surface is going down. And this is basically the flow velocity that is coming out, QT divided by the area of cross-section of this tube, A. Okay. So these are equal. Now, here height is reducing. So dH by dt will have a negative sign. Now, since this will have a negative sign, you have written QT in a such a way that it is having a negative sign. That's all. Otherwise, you could have written QT is PT minus PA over R. That is coming out. But you have written it this way to have a negative sign to match with the sign of dH by dt. So we say that dH by dt is Qt over A. Now this Qt you substitute from here is minus rho gh over R. So this is minus rho gh over R. Then if you rearrange minus rho gh over R, so you take R will come here, RA goes to the numerator in the left side. Rho g will come at the denominator. So Ra over rho g into dH by dt plus h equal to 0. So this is basically the typical first order system where the time constant is Ra over rho g, resistance of the tube into area of cross section of the tube divided by the density into acceleration due to gravity. If you have solved this, your solution should be like this. Your height of the liquid inside the chamber as a function of time should reduce like this. So initially it is h naught. When t equal to 0, it is h naught. And then it will exponentially decay, right? It will start with some h naught and then it will reduce something like that to 0. Okay. So if you know ht, you can actually know what is the qt, right? So if you know h, this h is a function of time. So you know what is the flow rate at that time point. Okay. So this is something that, this is how you can analyze fluidic systems that are first order in nature. Okay, so we talked about first order system. We talked about the general equation of a first order system and what is the typical response of a first order system. And we took examples from mechanical spring dashboard system. We took an example from electrical, that is an RC time constant RC system. Then we talked about a thermal system, and also we now took an example of a fluidic system where there is a tank containing water and you want to know how the height of liquid inside the tank is reducing with time or how the flow rate that is coming out is changing with time. Okay, so this simple system can be represented in terms of first order system. Now, we are going to revisit same mechanical, electrical, thermal, and fluidic second order systems. Okay, but before we do that, in today's class, we'll learn the basics of second order system, how we learned the basics of first order system. Okay, so in rest of the class, we'll talk about that. So if you take
Sir, I'm sorry to interrupt, sir.
Yeah.
Can I ask one question, sir, if you allow?
Yeah.
Sir, in the first order system, whatever system we have just read, like electrical, thermal, and fluidic, basically it was a homogeneous equation in that sense, right, sir? Like dy upon dt, some constant plus yt, and is equal to 0, right, sir?
Yeah. Yeah.
So if I have a like external like frequency, like external function like ft or maybe ut or whatever,
Yeah, that will be a second order system.
so that will convert to a second order system, sir.
Yeah, we'll talk about that in the next class probably. So when you have an external forcing function, when you have an inertial force, see here when you talked about the system here, we said that the inertia force is negligible, right? So the moment you have an inertial force, okay, you will see that this form of equation is no longer valid. Okay. So to analyze a system which has inertial force, you have to have a second order system. Okay. So you have
Thank you, sir.
acceleration terms coming here. That will be m times d square x over dt square plus the damping term and plus the stiffness spring constant term. So then that will be basically a second order system. Okay.
Thank you, sir.
Yeah. So the moment you have acceleration, you have to talk about a second order system. So this is the standard form of second order homogeneous system. You typically have 1 over omega n square d square x over dt square plus 2 xi over omega n and omega n is the natural frequency of the system and xi is called the damping coefficient. So a solution to this second order system takes a form something like this. You will have xt is some constant c into e to the power st, where if you substitute this into this equation, you can see that this will be 1 over omega n square. Your d square x over dt square will give you s twice. So that will be s square into c into e to the power st. Then second term will be 2 xi over omega n. dx by dt will give you s into c into e to the power st. Then your x is simply c into e to the power st. Now c e to the power st, you take it to the right hand side because the right hand side you have 0. So if you simplify, this equation will come like this: 1 over omega n square s square plus 2 xi omega n into s plus 1 is 0. Now you can notice your s is like a frequency term, right? We talked about the Laplace transformation, right? From time domain, we have gone to frequency domain, and a differential equation has become an algebraic equation. Okay, so this differential equation has become an algebraic equation in the frequency domain S. Okay. Now, since this is an algebraic equation, a root of this equation is like a quadratic equation, right? So a root to this equation will be, let's call it, takes this form. So S is basically minus sigma plus minus j into omega d, where j is basically square root of minus 1. Okay, and this is a complex term, and this is the real term. So basically, if you write down ax square plus bx plus c equal to 0, your x will be minus b plus minus b square minus 4ac square root over 2a. So this is exactly, what you get as the solution. Your sigma is basically xi times omega n, and your omega d is basically omega n into square root of 1 minus xi square. Okay, so these are basically expressed in terms of xi omega n into omega n into 1 minus xi square root. So this sigma is representing the attenuation. Okay, how fast, if you perturb a system, it is coming back to its original state. Okay, so that is the attenuation that we are talking about. How much resistance is offered by the system to an input. Okay, so that is decided by this term xi into omega n. And omega d is basically an algebraic representation of omega n 1 minus xi square, which is known as damped natural frequency. Okay, it is called damped natural frequency. Just a mathematical representation of natural frequency into some function of this damping coefficient. Okay. Now, the natural frequency omega n basically determines the time scale of the response. Okay, if frequency is small, that means the time scale will be large, and if the frequency is large, then the time scale will be small. And in this case, we just assume that the natural frequency is greater than 0. So if natural frequency is greater than 0, then the sign of sigma or omega d is basically decided by the sign of chi, okay, or the magnitude of chi. The damping coefficient basically decides the nature of the output. Okay. So if chi is less than 0, if the damping coefficient is less than 0, then such a system is always unstable. Okay. And in that case, the natural response grows in time without any bound. So you can see that when chi is less than 0, when chi is less than 0, that means sigma is negative. When sigma is negative, this term here has minus sigma, so this will be positive. When S is positive, when time increases, this term will only grow with time. That means you take a system and you subject it to input, and the response of the system will go crazy. Okay, it will go out of bound. There is no control over the system response. Okay, it will grow anything with time. Of course, this is something we do not want. So we really do not design a system with chi less than 0. If you have chi equal to 0, then such a system would be called marginally stable. That the natural response is of constant amplitude, and this is the undamped case. So if you take chi equal to 0, so that means this term becomes 0, and your omega d becomes omega n. Okay, so this becomes basically j into omega n plus minus. So that you substitute here. So you have e to the power plus minus j into omega n into t. Okay, so this is the case where you say that it is an undamped case. Okay, because your amplitude is still going to increase with time. Now, when chi is greater than 0, okay, of course, you design many systems when damping coefficient is greater than 0. Then, in that case, such a secondary system is called stable. Okay, because the natural see here, when chi is greater than 0, that means sigma is positive. Okay, and when sigma is positive, then minus sigma is negative. That means it will be e to the power minus of something. And in that case, when time t tends to infinity, definitely this right-hand side has to go to 0. So this is a stable system. Okay, so chi greater than 0 for a secondary system gives you stability. Okay. Now, such a stable case can be further subdivided into 3 possibilities. Okay. So if you have chi less than 0, you are gone crazy. I mean, the system is going to go without any bound. Chi equal to 0, this is an undamped case, but when chi equal to greater than 0, you have 3 possibilities. Let's call the first possibility, which is your chi is positive but lies between 0 to 1. That means it is something like 0.1, 0.2, 0.3, and so on. Then such a secondary system is called underdamped. Okay. And when we work in the frequency domain, the poles will have imaginary component, and the natural response contains some amount of oscillatory component. And if you have the lower value of chi, then the system will have more oscillatory responses. That means they will be more lightly damped. So value of Xi would decide whether it is oscillating frequently before it comes back to its native stable state, or it's very quickly comes back to its native stable state. So that is decided by the magnitude of Xi. But since it is 0 to 1, it is underdamped, but that it will not, very quickly come back to its stable response. But when Xi equal to 1, then such a second order system is called critically damped. Okay, that means you can see here when Xi equal to 1, then omega d is basically omega n. This is also omega n. Okay, so essentially you have a system where this is both the poles would lie on the negative real axis. Okay, because this term is going to go 0, and you will simply have here c into e to the power omega n into minus omega n into t. So you will have it both as no imaginary frequency will be there, only you will have real but in the negative axis. When Xi is greater than 1, then such a second order system is called overdamped. Okay, and the poles are at distinct location on the negative real axis. And here, this you can, as we are going to show later, that this system can be thought of as two independent first order system when Xi becomes 1. Xi becomes 1 is a case where there is no oscillation. Okay, you give an input, slowly the system will capture the output matching the input. Okay, there is no response. So this is like a first order system. Okay? The behavior is very close to first order system. But when Xi becomes greater than 1, you can see here that this term is now becoming, right? So you have some J coming here. Now already there is a J. So J into J gets multiplied. So they get minus 1. So you basically have no complex term. So that is basically a first order system. Okay. So, but since you get plus minus here and you have plus minus here, you have two values. So those are basically two independent first order system that we are talking about. Okay. Now, a general first or second order system is typically characterized by this relation. So you have the output, which is in the frequency domain Cs. This is the input in the frequency domain is Rs. And the output to the input is basically this function, which is known as the transfer function. And here, the omega n is basically the undamped natural frequency of the second order system, which is the frequency of oscillation of the system without any damping. Because if you make damping 0, then this is basically the frequency at which the system will oscillate. And Xi is basically damping ratio, which is of the second order system, which is a measure of the degree of resistance to change in the system output. Okay, so you give an input, how much the system will resist it before it actually gives an output. So you can actually, for a given transfer function, you can know what is the omega n and what is the Xi. So let's say somebody gives you this transfer function. Okay, Cs output to input is 4 divided by s square plus 2s plus 4. How do you know that? What is the natural frequency and what is the damping? So you compare this with this system here. Okay, so you bring out the Cs over Rs is omega n square divided by s square plus 2j omega n s plus omega n square. And you can see that your omega n square is 4. This is the general equation. This is the given equation. So omega n square equal to 4. So that means your omega n has to be 2. Now you work on the denominator. Already this is 2, so 2 square is 4. So you can write that s square plus 2 j omega n s into plus omega n square is s square plus 2s plus 4. Now s square get cancelled. And omega n square is basically 4, so they also get cancelled. So basically you have 2 j into omega n s is 2s. Okay, this term is same as this term. And omega n is already 2, s get cancelled. So your chi into omega n becomes 1. That means your damping coefficient is 0.5. Okay. So for any kind of second order system, you can actually know what is the natural frequency and the damping coefficient if you compare it with the general expression of the second order system. So if you have, this is the output by input, this is the transfer function. The poles are determined by equating the denominator to 0. Okay, that is how the poles are, system poles are determined. So if you say this is like a quadratic equation, s square plus 2 j omega n s plus omega n square equal to 0. And you can find s is like ax square plus bx plus c equal to 0. You have minus b plus minus b square minus 4ac square root by 2a. So if you do the two roots of the equation, which are called the two poles of the system, is minus omega n j plus omega n into j square minus 1 square root. The other root will be minus omega n j minus omega n into j square minus 1 square root. So these are basically called the two poles of this system, the current system. What does it mean? So in an overdamped case, so you write the two roots here. According to the value of j, you can have 4 different categories. When j is greater than 1, the system has 2 real distinct roots, right? Because j is greater than 1. So this will be basically square root of a positive term. This will be also square root of positive term. So it will be minus plus, this will be plus minus, this will be minus plus. And basically, you have the poles coming as real in the x-axis, right? Because your sigma is basically, I mean, this is real because j is greater than 1. So they can be located in the negative x-axis because j square minus 1 square root will be less than j. So when it is positive, this will be less than j. So omega n into a parameter factor which is less than j will be less than minus j omega n. This term will be dominant. So of course it will be somewhere here. Now here we are talking about this term which is positive. And then you have a negative here. Then you have negative here. So basically you will have this. So 2 real distinct poles are going to be on the x-axis when you talk about the overdamped case. That means j is greater than 1. Now, if you take an underdamped case, when the system has two complex conjugate poles, because when j is between 0 to 1, this will be less than 1. That means when you take square root, you will get a complex number. Okay, you are going to get a complex number. So that means the solutions are no longer real. They will have a real part. They will have an imaginary part. So that means the roots are going to lie somewhere here and somewhere here. Why? Because this x-axis is the real part, which is always negative. The imaginary can be positive or negative, depending on whether it is plus or minus. So they would basically lie in the second quadrant and the third quadrant. I will just stop in the next two things we'll discuss. We talked about critically damped when damping coefficient equal to 1. When damping coefficient equal to 1, the entire term here is 0, right? This is I is 1, so this term vanishes, this term vanishes. So you have basically two poles which have the same magnitude. So basically they overlap here, minus omega n into chi. So they are overlapping here. And when you have a case where it is 0, that means your damping coefficient is 0. So this is basically 0. This is 0. So this square root of minus 1, that is I into omega n or j into omega n. And this will be also I into omega n or j into omega n. And chi is 0, so there is no real part. This term goes completely. So it will be plus j omega n minus j omega n. So it will be, one will be in the positive y-axis, one will be in the negative y-axis. So you can see that how you can nicely represent all these four different cases, right? Overdamped, underdamped, then undamped, and critically damped in the pole plot, right? In which axis they, whether the real axis or the imaginary axis. So I will stop here, and if you have any question, we can discuss.
So basically, for the critically damped system, hello.
Yeah.
So will there be any oscillatory component or not?
Just give me 1 second.
Yes, sir.
Recording stopped.
Yeah, you said for
For
which
the
case you said?
when j is equal to 0, sir.
So
Sorry,
when chi equal to
j is equal
0,
to 1, sir. J is equal to 1. That means when the system
when
is
chi equal to 1, see, you will have just simply, this term will completely vanish.
so only real root will
You
be there.
have
Okay.
minus omega n and minus omega n. Okay. So if you go to your system response that we talked about, so your when it is this, basically it will be omega n because this term goes to 0. So this will be c e to the power minus omega n into t, right? So it will basically nicely decay with time. Okay. So it will decay with time like a first order system. There will not be any oscillation as such because there is no complex term here.
So oscillation will happen only if the complex term is there, right, sir?
Yeah. Otherwise, it will become a first order system basically.
Thank you, sir.
Okay.
ठीक है,
Because
sir.
first order system is only real, right? And it will nicely decay. But the only problem is that when chi is greater than 1, then things will grow. And that is not a first order system. I mean, if you perturb it, it will become highly unstable and you have no control over the system. Typical example, like an atomic reaction, right? So you don't have any control over the process.
And one more question I want to ask you, sir. Basically, like whatever system we have read till now, like thermal and fluidic and what I mean to say is electrical system. So there have a lot of assumptions in that. Like for thermal, we had like assumed that the heat transfer will happen only in one direction. Then there are so many assumptions. So basically,
Yes,
sir,
yes.
so basically, we are deriving a theory basis of assumptions which is not really happening in the real world, and then we characterize our what I mean to say is measurement system basis that will not be adding up the errors in a much bigger way.
Yeah. So, I mean, you have a very good point. So typically, I mean, if you have let's say an iron ball inside a oven and you try to bring it out and you want to know how quickly it will cool down. you are using a first order system and you are saying that, okay, I mean, I am trying to characterize and but I have made so many assumptions, right? And how accurate it will be. So typically, that is why the time constant is something that ideally when you wait around the time constant, then the system should reach steady state. But in a first order system, it actually takes 5 times the time constant. Okay. And depending on the problem, again, if you have a highly complex system where first order system fails, then you, of course, your predictions are going to be far off. Okay. That is why when you have a thermal system which requires second order analysis, and if you do first order analysis, of course, you are going to be very far off. So, I mean, probably next class we'll look at a second order thermal analysis system. So in that case, you have, either a heat source or you have a heat loss. And there, if you use this first order formulation, of course, you'll be making an error. The error could be very large. So, but most of the thermal systems, these assumptions are valid. And in fact, your predictions come out to be correct. It really depends on the system that we are talking about. There is no general, guideline as such.
Thank you, sir.
Thank you, sir.
Yeah. Okay. So thank you all,
Thank
and
you, sir.
we'll meet Wednesday.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
So I'm sorry, I was in class, so I could not receive you well, sir. Please. Okay, sir. Thank you, sir. Thank you, sir. Okay, sir.